In this lecture, we will continue our discussion of clinical data standards. As with the last lecture, we will focus on this center part of the core content outline and the various types of clinical data standards in clinical informatics. In the last lecture, we focused on the first four items through messaging standards. In this lecture, we'll continue on with nomenclatures, vocabularies, and terminologies, ontologies and taxonomies, and interoperability standards that bring everything together. The last type of standards we'll discuss are terminology standards. Obviously, an important area because the benefits of computerization of clinical data depend on our normalizing the data. Of course, clinical language is inherently vague, sometimes by design, and this can be at odds with the precision of computers. So for an example, as clinicians, we know that the words cancer and carcinoma mean the same thing, but inside the memory of a computer, they're no more similar to each other than apple and zebra. It's also been said that medicine should have fewer words and more meaning, like the more constrained language used in air traffic control and in the military. But instead, in medicine, there are very few restrictions on the language of clinicians. There are a number of resources around terminology standards. A recent book released by Gianangelo is a nice overview of all of the different terminology standards that are available. There's a lot of terminology when it comes to terminologies, and the definitions of these terms should be understood. Let's start with terminology itself, typically a collection of terms, but that's actually not quite accurate, as terminology means many different things to different people. Let's start with the idea of a concept, which is a thing or an idea. And of course, a concept can be expressed by one or more terms, whether it's a disease or a physical finding or a treatment. There are often more than one way to say the same thing. When we have multiple terms for the same concept, those are called synonyms. And of course, there may be instances when a word or a term has more than one meaning. That's a polysem. We may encounter a dictionary that has concepts plus the meaning for each concept. There's also a thesaurus that typically groups synonyms by concept. And we may have a vocabulary that's a collection of concepts and terms in a domain. A final term that's important to know is ontology, although this term is frequently misused, but an ontology is a structuring of concepts and the relationships between them. One of the most articulate spokespeople for standardized terminology is Dr. Chris Shute. He has specified a number of use cases for standardized terminology. Obviously, one is information capture, so we can document findings, conditions, and outcomes. Another use case is communication, where we transfer information. Another use case is knowledge organization, where we want to classify diseases and treatments, perhaps putting them into categories of like conditions and like treatments. Also, a use case is information retrieval, where we access knowledge-based information in the medical literature or textbooks or websites. And finally, decision support. Implementing decision support rules is more precise when we have standardized terminology. Much harder for computers than humans. Humans actually understand synonyms and polysems pretty well. So for example, with synonymy, how many different ways can we say common cold? In a medical record, we may encounter terms like cold, upper respiratory infection, URI, pharyngitis, bronchitis, rhinitis, and even viral syndrome. And we as humans tend to understand that relatively so. And likewise, how many different ways can the word LEAD be used in medicine? Well, it can be a verb, hypertension leads to heart disease, an EKG lead, the chemical lead poisoning, and so forth. And again, as humans, we can oftentimes look at a word in a sentence and understand its context, but computer programs don't always know how to do that. If we wish to standardize terminology in medicine, we obviously need standardized medical vocabularies. There are many such vocabularies used for a variety of purposes, and they usually have some sort of hierarchical structure as well as some sort of coding scheme. Ultimately, we want to represent the concepts in these vocabularies as codes that enable their easier processing with computers. A leader in this area has been Semino, who has described a number of desiderata for standardized medical vocabularies. In terms of the codes, there are different approaches that are taken. There can be numerical codes where they're assigned sequentially or randomly in some sort of order. There may be mnemonic codes where there's an abbreviation for the concept. Sometimes codes will incorporate hierarchical information so we know where in the hierarchy they are. There may be composite codes that use juxtaposition of different codes or even some sort of ordering in combination. One key aspect of codes that Semino and others emphasize is important, as we should avoid semantic codes, putting meaning into codes. For example, mnemonic codes that may express what the actual meaning of the term is, because the meaning of the term may change. Some additional issues with terminologies and coding. Rosenblum has noted that there are different categories of terminology representing different uses. There is interface terminology that helps with data entry. There is processing terminology that optimizes for tasks such as natural language processing. And then there's reference terminology that enables storage, analysis, and retrieval. Coding is an important part of healthcare, and it has historically been an activity of the Health Information Management, or HIM, profession. Of course, with the growing uses of codes and the changes in technology, this is a field in a state of flux. And we increasingly see applications like computer-assisted coding that help assist human coders with computer programs. This slide shows the different terminology standards that we'll look at pretty much in the rest of this portion of the course. They are organized along the lines that the Gianangelo book is organized. So we'll look at standards for diagnoses, for drugs, for laboratory, for procedures and diagnostic study. We'll talk about nursing standards, literature, indexing standards, devices, and then we'll also look at some comprehensive terminologies and then review a few others. The first terminology in medicine was ICD, which is now called the International Classification of Diseases, although originated in 1893 as the International List of Causes of Death. And the first purpose of ICD was to compile mortality statistics. It was eventually taken over by the World Health Organization and expanded to code diseases for more than just cause of death, and that's when it became known as the International Classification of Diseases. The version of ICD used until relatively recently in the United States was ICD-9. ICD-9 actually was approved by the World Health Organization in 1975. It was organized hierarchically with one digit for each level of the hierarchy and going out 4 codes. The United States modified ICD-9 to Icd-9 Cms, with the Cm standing for clinical modifications, which added more detail and 5-digit codes. Icd-9 Cm also had some other codes. It had V codes for encounters that were related to prevention and screening, so one could talk about colorectal cancer screening without stipulating that that diagnosis was actually present, and also G codes that documented provision of certain services, such as quality measures. Icd-9 Cm was used in the United States until 2015, when the transition was made to Icd-10-Cm. There is, of course, still a lot of data that is encoded in Icd-9 Cm. This slide shows an example of the Icd-9 Cm hierarchy for different types of pneumonia. There are a number of limitations of Icd-9 that have been well described by Shute. Most of these stem from the use of codes that state things like not otherwise specified or not elsewhere classified. The not otherwise specified codes are usually a wastebasket that include other things that have not been specified, and there is perhaps no better example of this than, over the years, the evolution of our understanding of viral hepatitis. When some of us trained, the term non-A, non-B hepatitis was used, but of course, over the years, we've discovered hepatitis C, hepatitis D, and many others, and so non-A, non-B hepatitis may change over time. So these unspecified terms may change over time. There are also not elsewhere classified codes that indicate that there's no separate specific code available to represent the condition that is documented. For example, depressive disorder, not elsewhere classified, is used in Icd-9 for any type of, quote, non-major depression. Another limitation of Icd-9 is the use of digits in codes, meaning that there can be no more than 10 items at a given level. There are some conditions for which there are more than 10 items at a given level in the hierarchy. Another limitation of Icd-9 is that the granularity is often inadequate. For example, there is one code for most types of cancer in a given location, and of course, a single cancer can have many different histologic types and behave in many different ways. And Icd-9 is not extensible. We can't add modifiers for location or severity, and we can't indicate any kind of causal relationships. Icd-10, despite its relatively recent adoption in the United States, has actually been around for quite some time. In fact, it was released by the World Health Organization in 1990, and it made substantial changes to the structure from Icd-9. And it was adapted in the US as Icd-10-Cm, and after numerous delays from 2011 through 2015, it was finally adopted in the United States in October of 2015. Also at that time was the release of Icd-10 PCS, which added procedure codes, mostly inpatient-based, with CPT-4 still used for coding outpatient procedures. The Icd-10-Cm adaptation had up to 7 levels for diagnosis codes and also 7 levels for procedure codes. We'll look at both. And there was also a general equivalence mappings, or GEM, that allowed translation from Icd-9 Cm. There are many differences between Icd-9 Cm and Icd-10 Cm. Icd-9 Cm has a little more than 13,000 codes, and Icd-10 Cm nearly quadruples that. Obviously, the codes need to be longer so they can be extended up to 7 characters. Whereas Icd-9 Cm codes are mostly numeric, with the exception of the V, G, and E codes. ICD-10 has the first character as alpha, characters 2 to 3 as numeric, and characters 4 to 7 as able to be alphanumeric. The specific location of the character indicates different aspects of the code in both Icd-9 Cm and Icd-10-Cm. Icd-10-Cm addresses one of the limitations of Icd-9 Cm, which is granularity, and it does this on a somewhat massive scale. For example, the unspecified adverse effect of other drug, medicinal, and biological substance is extended out to essentially every category of drug, whether it's the initial encounter or a subsequent encounter. In fact, there are nearly 200 codes now for adverse events related to drugs. Icd-10 PCS likewise massively extends out the number of procedure codes. And they too have location of numbers and letters in various parts of the code to indicate aspects of the procedure. And granularity is also an issue for Icd-10 PCS, with the Icd-9 code for pericardectomy and the many Icd-10 PCS codes for various operations related to removing the pericardium in an operation. Some have argued that this excess granularity reaches a point of absurdity. For example, there is a code for one who is struck by a falling object on board a watercraft, and there's a different code for each type of watercraft, and unfortunately, an unspecified code for any other type of watercraft. Some of the detailed codes of Icd-10 have also invited artistry. There's a website that offers a book and PowerPoint slides on various health IT individuals who have taken a stab at illustrating various codes such as sucked into jet engine, subsequent encounter, and passenger and 3-motor vehicle injured in collision with 2- or 3-wheeled motor vehicle in non-traffic accident sequela. Some more about Icd-10. About half of all the codes are related to the musculoskeletal system, primarily injuries, and this is not surprising given the highly granular nature of the vocabulary. About a quarter of all codes are related to fractures, and over a third just distinguish laterality, left versus right. Therefore, the fields that are most impacted by the transition to Icd-10 are orthopedics, obstetrics, gynecology, and behavioral health. Primary care has a medium level of impact, and many of the medical specialties have a low level of impact. There are many informatics concerns over this excess granularity and whether we might transition to a more extensible or compositional terminology system, such as Snomed, or Icd-11, which is under development and based on Snomed. Some have argued that this may be a better approach than moving to Icd-10. In addition to cost concerns, there actually are informatics concerns about Icd-10-Cm. One we've already talked about concerning its perhaps excess granularity. Many in informatics would argue for the transition to a more compositional terminology system such as Snomed, or even Icd-11, which will be based on a derivation from Snomed, and that might be a better approach. although the downside is that ICD-11 itself will not be available until 2017, and then probably take additional years to develop a version for the US and get implemented in the US healthcare system. Some of these informatics concerns were brought out in an analysis by Boyd, who found that 36% of all mappings between ICD-9 Cm and ICD-10-Cm were convoluted, meaning that they weren't direct N-to-1, 1-to-1, or 1-to-N kind of mappings. And these convolutions varied by specialty, being about 5% for hematology and 60% for obstetrics and injuries. Another terminology standard related to ICD is the Diagnosis Related Groups, or DRGs. The original intent for DRGs was to aggregate ICD-9 codes into groups that would actually be used for health services research. The idea is that the many diagnoses would be lumped down into several hundred codes that represented the amount of resources required for treatment. DRGs were quite appealing to HCFA, the forerunner of CMS in the 1980s, as it developed its prospective payment for hospitalization program under Medicare. The DRG categories will stay the same initially under ICD-10-Cm. There will be many mappings into the individual DRG codes, but this may change later. This slide shows some examples of DRGs for respiratory diseases. Another terminology standard is Current Procedural Terminology, or CPT, in its current version of CPT-4. This is a classification of procedures performed by physicians, and a provision of a CPT-4 code is usually required for reimbursement not only by the government, but also private insurance companies in the US. There's a portion of CPT that deals with evaluation and management codes. These document the intensity of office visits for physicians. CPT was developed and is maintained and copyrighted by the American Medical Association, which means that it's not freely available and royalties must be paid to the AMA for its use. Another procedure coding system is the HCFA Common Procedure Coding System, or HCPCS. And actually level 1 of HCPCS is actually CPT-4. Then level 2 adds items and supplies and non-physician services. And there was formerly a level 3 that allowed adding of local codes, but these were actually abolished under rules from the HIPAA legislation. With the coming adoption of ICD-10, professional fees and outpatient procedures will be billed using CPT-4 and HCPCS, and inpatient procedures will be billed using ICD-10 PCS. And of course, ICD-10-Cm diagnosis codes will be required for all these. Another important area of terminology is drug terminology. There are a number of different code sets which sometimes make the picture confusing. The terminology around drugs is mostly led by the US government, and it has an initiative called FedMed, which is an interagency collaboration on an agreed set of standard, comprehensive, and freely accessible federal medication terminologies. And these terminologies include, which we'll discuss in the coming slides, the National Drug Codes, or NDC, the Unique Ingredient Identifier, or UNII, the National Drug File Reference Terminology, NDFRT, the NCI Thesaurus Structured Product Labeling, or SPL, and then a system called RX Norm, which includes RX terms. The original drug terminology system was the NDC. This is an 11-digit code that is assigned to each and every pharmaceutical preparation that is sold on the market. The first 5 digits represent the manufacturer, and this is assigned by the Food and Drug Administration, so companies such as Merck and Pfizer. The next 4 digits represent the product name, strength, and dose form. And there's one code for all variants of these within a manufacturer. The problem is that a different manufacturer who produces the same drug will have a different middle 4 digits, so that one doesn't necessarily know all forms of a drug unless one has the mappings from the different manufacturer to their product name, strength, and dose. And then the final 2 digits are used for packaging. For example, when it's a bottle of tablets, the number of tablets. The FedMed initiative maps the NDC codes into other terminology systems, so somewhat alleviating this problem with the middle 4 digits being different for the same drug produced by different manufacturers. Some of these other terminology standards, so there's the unique ingredient identifier that specifies ingredients in drugs and other compounds. The NDFRT is produced by the VA, and it further maintains mechanism of action, physiologic effect, and structural class of drugs. The SPL maintains pharmaceutical dosage form, route of administration, and potency. And then RxNorm attempts to provide a semantic structure for formulations of drugs and their components. There's then an RxTerms system that provides the interface terminology to RxNorm, and the combination of RxNorm and RxTerms now is emerging as a standard into which other drug terminologies must map. This busy figure demonstrates that all of the information, the semantics about drugs, can be captured in the RxNorm structure. And this figure shows the relationship among the types of information that is covered in the different federal drug terminologies, as well as the specific terminology systems that have the information within each. Another terminology standard is Logical Observations, Identifiers, and Numerical Codes, or LOINC. LOINC evolved as a way to describe the findings of laboratory tests, and it has been gradually extended to other types of tests, and it's also been translated into other languages. LOINC consists of observations. Each observation has a component or analyte, so that's the substance or entity that's measured or observed. And each analyte has a property, such as its mass concentration or numeric fraction, a time, a specimen, where it comes from, a scale in terms of how it's measured, and a method for making that observation. This slide shows a number of examples from LOINC, and we see different types of analytes that are measured in different ways. One of the challenges with all of the terminology standards we've discussed so far is that they represent different categories of terms, such as diagnoses and lab tests and procedures. Another approach has been an attempt to have a terminology for all of medicine, and the Snomed clinical terms, or Snomed CT effort, tries to do that. Snomed stands for Systematized Nomenclature of Medicine. It was originally developed by the College of American Pathologists. In fact, it was originally developed as a classification for pathology. when it was the Systematized Nomenclature of Pathology, or SNOP, and then it was extended to all of medicine in the 1980s. There was actually a related project going on in England, the Clinical Terms Project, and that project merged with Snomed to become Snomed CT. The ownership of Snomed was transferred to the International Health Terminology Standards Development Organization, or ITSDO, and Snomed has been translated into a number of different languages, and it continues to be translated into more. One of the challenges in the past with Snomed is that it was owned by the College of American Pathologists, who devoted considerable resources to developing it and wanted those who were using it to pay a license fee. In 2003, the National Library of Medicine negotiated a license for Snomed for all of the United States, and this license has continued with the transfer of Snomed to ITSDO. The NLM license allows Snomed to be freely used in all public and private entities within the U.S. for any healthcare, public health, research, educational, or statistical use, and a number of other countries have similarly licensed Snomed CT at the national level. And so basically, Snomed can be used to encode patient-level data sets and even redistribute them, as long as users cannot extract significant portions of Snomed from the data set. For those interested in more about Snomed, there is plenty of documentation, including a very readable starter guide. Snomed clearly is the richest vocabulary for describing clinical observations and findings, and its key feature is this multi-axial or compositional approach where terms can be combined, modifiers added to create more comprehensive terms from individual building blocks. Snomed contains a little over 300,000 concepts and about 1 million descriptions or terms that express those concepts in different ways, and also another 1 million relationships between concepts. This slide shows the overall design of Snomed. It can be somewhat daunting, but if you work through the various elements on this slide, you can obtain a general understanding of how Snomed CT works. Like all terminologies, everything emanates from concepts. Snomed concepts occur within hierarchies, which are broad general categories like body structure, clinical finding, procedure, etc. Within each of these hierarchies are, in essence, templates that have data elements that make up the concept. Snomed descriptions are the canonical or preferred terminology for a given concept, and then there are synonyms to those descriptions. There are also relationships, and some of these relationships are attributes. So, for example, an arthropathy is a joint finding, and appendicitis has associated morphology, in this case, inflammation. These relationships are what enable the more complex concepts to be built up from simpler ones. Although Snomed allows these complex expressions built up from simpler ones, it also has some terms that are pre-coordinated. What that means is that these more complex terms are brought together and part of the actual vocabulary instead of being built up from those simpler terms. There are also a number of nursing vocabularies, and within nursing are challenges that result from having multiple different vocabularies that have evolved for multiple purposes. So these different nursing vocabularies have irreconcilable information models, terms that are not always used the way that clinicians express them. They can be tedious to use in patient documentation, and then there's always a question of whether data is transferable across different settings. This slide shows the major nursing vocabularies and whether they contain terms for diagnosis, intervention, and/or outcomes. All of these vocabularies are included in the Umls Metathesaurus. In the 1980s, the National Library of Medicine recognized that we needed to reconcile these different vocabulary systems, and they launched the Unified Medical Language System, or UMLS project. There are three components of the UMLS project: the Metathesaurus, which we'll describe in the following slides. There's also the semantic network, which establishes generic relationships between the semantic types, or the high-level concepts. And then there's the specialist lexicon, which is designed to assist in natural language processing applications. Sometimes the UMLS Metathesaurus is synonymous with people saying the UMLS. The other components are relatively small relative to the Metathesaurus. What is the UMLS Metathesaurus? Well, from its documentation, it's a database of information on concepts that appear in one or more of a number of different controlled vocabularies and classifications used in biomedicine. So in essence, the Metathesaurus is a meta-thesaurus among terms across the different vocabularies. So whereas a thesaurus might be within a vocabulary, a metathesaurus is across multiple different vocabularies. As such, synonymous terms from different vocabularies are given the same concept identifier, and then each distinct terms has different lexical variants, also known as strings. There is some jargon associated with the UMLS Metathesaurus, but it's important to understand this jargon to understand what the UMLS Metathesaurus is about. We'll define the jargon in this slide and show an example of it that illustrates it in the next slide. Remember that the goal of the UMLS Metathesaurus is to link concepts across different vocabularies. So a single concept that occurs in multiple vocabularies has a concept unique identifier, or CUI. Within these different vocabularies, there are source terms for that concept that are relatively similar. They differ only in lexical variations, such as word order or plurality. These groups of terms are linked by the term unique identifier, or also called the LUI. And then within each of those terms, there are lexical variants that are strings, and they're grouped by the string unique identifier, or SUI. And ultimately, each string is an atom that comes from its source, the atomic unique identifier, or AUI. So here's an example of a concept in the Metathesaurus. Let's look at the concept of atrial fibrillation. There are different terms for atrial fibrillation, such as auricular fibrillation, and then the various abbreviations, AF, AFib, with and without a space. And then within each of those terms, there are different strings that are the lexical variants that vary in either word order or plurals. Each of the terms will have a different LUI that maps to that single CUI for atrial fibrillation. And then within each LUI, there will be multiple SUIs that map to the terms. And then each of those terms, as they occur in the original source vocabulary, will have an AUI. There are a number of limitations of the UMLS Metathesaurus. First, it only maps one-to-one relationships. So if there's one term in one vocabulary that could map to multiple terms in another, that mapping will likely not be present. The Metathesaurus doesn't add any new terms. The only terms that can be used are those that come from the source vocabularies. The Metathesaurus has no unifying hierarchy itself, although it maintains information about the existing hierarchies in the source vocabularies, and it's not extensible in the ability to add qualifiers and relationships in the sense of Snomed. For these and other reasons, the use of the Metathesaurus is modest at this point, and it may actually derive its value as being essentially a repository for vocabularies where we can learn about terminologies and the specific terms within them. There are some other healthcare vocabularies worthy of mention listed on this slide. One is the common dental terminology, which is equivalent to CPT, but for dentistry. There's also the medical subject headings or mesh vocabulary. We'll talk about that vocabulary when discussing information retrieval. There's the universal medical device nomenclature, which provides naming for medical devices. There's the Diagnostic and Statistical Manual of Mental Disorders, or DSM, a sometimes controversial classification of psychiatric and psychological disorders. There's the International Classification of Functioning, Disability, and Health, which, as the name implies, focuses on areas of function and disability. There's also the International Classification of Primary Care, or ICPC, which classifies the activities of primary care. There are other terminology activities worth noting. One is the development by the National Institutes of Health, which funds most biomedical research in the United States, of common data elements for research studies. The idea is to create common elements that researchers in a given area can use so their data will be more comparable. There are many of these listed on the website linked here, but some examples of them are the patient-reported outcome measurement system, so measures of patient-reported outcomes. In the area of neurologic disease, the National Institute of Neurologic Disorders and Stroke has a Common Data Elements project. There's a global rare diseases registry that has common data elements, and then also consensus measures for phenotypes and exposures. Another body of work is that devoted to clinical element models. The idea being that just collections of codes can be ambiguous and that we really need models for clinical elements. And so the Clinical Information Modeling Initiative, or CIMI, attempts to create these clinical element models for clinical data. This work was advanced through the ONC SHARP-N project that was focused on secondary use of clinical data. And probably the most experience with their use comes from Intermountain Healthcare in Utah. There are some commercial efforts related to terminology. These efforts take different forms. For example, there's Intelligent Medical Objects, or IMO. They provide mapping, updates, and access to all of the different terminologies that we have just described, such as ICD, Snomed, and others. There is also the medicine terminology that is focused on clinical documentation at the point of care and electronic health records, and another terminology system that was originally developed by 3M and has been moved into an open source model called HDD Access. We've presented a lot of different standards. in these lectures, and how do we bring it all together? Remember that what we're ultimately aiming for is semantic interoperability. Perhaps a good definition of this is that any computer utterance in one computer system has the same effect in another. What is the likely direction that will go? Well, the ONC Interoperability Roadmap, the JSON Task Force Report, the Argonaut Project, and so forth have laid out a clear path, and this is being followed by ONC and others. We will have communications using RESTful architecture over the internet. It's likely that FHIR will emerge as the standard way to structure data, and we'll have APIs that move FHIR data back and forth between different applications, whether they're running on servers or on our smartphones or computers or any other device. There will be the use of OAuth 2 and OpenID for security and authentication of individuals, and there will be the two major types of data. There will be documents that we historically use in healthcare, specified by the standards from IHE and the consolidated CDA. And then there will also be discrete data, initially the meaningful use common data set, and then expanding with Snomed CT and other terminologies. What about additional readings on standards and interoperability? These have already been mentioned, but just to review them here, there is the chapter by Hammond in the Shortlift textbook on standards. There are also books themselves, the Giannangelo book on terminology standards and the Benson book on interoperability standards, including Snomed CT, HL7, and FHIR.